psychic energy. I don't know if you guys know this.
Maybe
Chi.
Chi.
Chi master. And the people who can control this mysterious energy can do all kinds of strange things. And I can, for example, I have heard, do a handstand on one finger and do things that ordinary people cannot do. But I learned to do one thing by controlling my chi, which is to break a pencil with a folded dollar bill. So if you take a dollar bill and if you fold it in half, like this, and you fold it in half again, then you have a kind of a thing like this. And it's not very strong. Okay, so you try to hit something with it, it's just bent. But if you can focus your chi, then it's possible to make this so stiff that you can break a pencil with it. Can any of you do this?
I can do this.
Can you do it? Really? Do it. It's nice to have another chi master.
Alright, well, will you hold the pencil for me?
Well, you need a volunteer.
Alright, who can hold a pencil really sturdy? Alright,
I usually give a karate
I
shot
can
when I
see,
do
I
it.
can see everything. I can't see. Hold on, give me some room here. It's been a while since I've done this, so I might I'm feeling distracted, so we'll see. Alright. The finger?
There we go. I didn't know they had these towels.
Do you have any more pencils?
I don't have any more with me. Okay, I welcome all of you guys if you have interesting tricks. We can always spare a couple of minutes.
If someone can stand on one finger.
Fingers, yes. You know?
I said if somebody can stand on one finger, you could demonstrate.
Yeah, I wish. Yeah, I haven't been able to progress that far. Okay, so now we start a really important thing. I want to talk about. Okay, this is really at the very heart of statistical mechanics, and there's different ways of doing it, but we will do it considering something called a canonical ensemble. And canonical just means kind of fundamental, and ensemble just means a collection of things. So, and probably you have seen this before, but I want us to think about a collection of n systems, so curly n, so imagine that you have a very large number of identical systems and n particles, little n, per system. So what should you be thinking of? A nice example is, imagine a little glass cell of liquid crystal. And kind of ignore the glass. Just suppose you have a little slab of liquid crystal somehow contained in some region of space. That is your system, each of which consists of n particles, where n is 10 to the 23, very large number. And we have lots of these guys, okay, lots. And we put them all into a big box. And this big box is a supersystem. So imagine that you have a huge box, and it's all insulated, so nothing can come in or out. Energy cannot go in or out. And then in here, we have all these systems. So this is a system. So one of these guys is a little liquid crystal slab containing lots of molecules. So that's a good way to think about this. Now, we can assume that energy can flow from one of these systems to the other, but the total energy in the box is a constant. So total energy is a constant, but energy can go from one system to another. So what we want to imagine then is that we have a super system somehow, and with a certain amount of energy in here, and that energy has to be distributed among these systems. All the energy could be in this guy and no energy in the others, or we could have 10% here, 5% here, and like that. So there are many, many ways that the energy could be distributed among these systems. And we're going to ask, what is the most likely distribution of energy? What is the most likely distribution of energy? If you think about all of the energy being only in one box, then there's only n ways to do that. Right? We can put all the energy in here, or in here, or in here, or in there. But if we break up the energy into smaller pieces, there are more ways to do it. So we're just going to try to figure out what is the most, what is the most likely distribution that the energy can take. That is, what is the configuration which can happen the most number of different ways. You can imagine that you have, instead of this physics picture, suppose you have a town, a village maybe, with walls, nobody can go in and out. You have people living inside, and they have money. And the money can be distributed many ways. All the money can be in one guy's pocket. Okay, but life goes on, and the guy buys bread from the other guy, and so money flows between them. And then you could ask, what is the most likely way that the money is distributed? And that is just the largest number of ways that you can arrange to have the money, whose total is a constant, distributed among these people. So that's what we're going to try to do. So we're going to ask, how many ways? Okay, so yeah, let's suppose that, should I follow the notes here? Suppose that there are, I made a notational thing. This should be capital N. That's my problem. This is curly capital N, this is ordinary capital N. Now suppose that N1 systems have energy E1, N2 systems have energy E2, and like that, just continue. Of course, we must have that all these N's must add up to curly N. And all of these energies must add up to the total energy. But let's just suppose that we have some arrangement like this. We have 3 systems that have 2 joules of energy and 15 systems with kilojoules, stuff like that. And then we can ask, how many ways can we make this happen? How many ways can I put 3 systems with energy E3 into this thing? So how many ways? do this. And so basically now this is just a question of how can I distribute N1 systems of energy E1. I mean, I can put one here, one here, one here, one there. Then how many ways can I do the next one? So we just have to try to count all these things. And then we will know how many ways we can distribute the energies in this way. And then we can ask, well, what about some other distribution? How many ways can we do that? And then we'll ask, which distribution is the biggest? Which is the thing that we can do in the largest number of ways? And we'll argue that other things being equal, that is what we're likely to see in an experiment. So, I'll erase all this now. And so let's ask, first of all, how many ways can I put energy E1 into N1 system?
C curve N1.
Okay, so suppose that N1 just for now is 3. Okay? And we want to know how many ways we can put, I don't know, say this is 1 joule. How many ways can I put these 3 1 joule clubs into the system? Right? Well, I take the first of these, right? I take 1 joule, and I can put that into the first box, the second box, third box, and so on. So I can do that n ways. Right? So imagine that I have 3 balls, right? Instead of energy, suppose I have balls. Suppose I have 3 balls, red, yellow, green, rubber ball. Okay, how many ways can I put this into this super system? Imagine that the systems are just empty spots where I can put a ball. I can take the first ball, red, green, blue. I take the red ball, I can put it in the first hole, or I can put it in the second one, or the third one. Right? I can do this n different ways. That's just the first ball. Right? The second one, so I now take the green ball, and I can put that in n minus 1 ways, right? Because one of the boxes is now already full. And the next one, I can do in, n minus 2 ways. So this is how many ways I can put in these 3 balls. Now, one way of writing this is just to write this as n factorial divided by n minus 3 factorial. The other thing is that the balls that we are putting in are different, red, green, and blue. But the energy is not different. So if I were to interchange 2 of those balls, it wouldn't make any difference. If I were to interchange 2 of them, it would make no difference. So we have overcounted, because we can make these interchanges, right, which are equivalent. So we have to divide this guy by 3 factorial, and this guy by 3 factorial. So the number of ways, let me erase this. So the number of ways of distributing N1 objects in units of energy, N1 indistinguishable objects, is curly N factorial divided by N1 factorial divided by curly n minus n1 factor. Okay? That's what we have on the board. Instead of 3, I'm writing n1, could be anything. Okay? All right. Okay, so suppose we have done this. Now I want to move on. I want to distribute these guys. How many ways can I do that? Well, it's the same as before, but the number of empty spots now is
minus
curly and minus that, right? Then n2 objects, I have to multiply this, right? Because we're multiplying these things together, because for every one of these events, I have another event. And then it's going to be the same story, except that I have to have n1 here, and then n2 here, and then n minus n1. So I have to make the number of available boxes smaller, minus n2 factor. Right? Is everybody still happy? This is the same result as this. We are just replacing curly n by curly n minus n1. And then if we continue this, we just keep on going. N minus n1 minus n2 factorial. Here we have n3 factorial and n minus n1 minus n2 minus n3 factorial. And a really nice thing happens that you should all rejoice at. We have these nice cancellations. And these guys cancel. And it just goes on like this. And at the end, you know, this guy is going to be 1. Factorial of 0 is 1. So in the end, we find that the number of ways we can distribute these specific lumps of energy, this many of that many of that, is just equal to n factorial divided by n1 factorial, n2 factorial, n3 factorial, and like that. All the way from here. Now, imagine that the universe is filled up with these supersystems, you know, where every possible outcome is equally likely. Then we will find supersystems with all the different, so one distribution of energies corresponds to the set of numbers n1, n2, n3, n4. You can imagine that the universe is full of these supersystems where each distribution, each individual distribution is equally likely. Then we will find certain situations, rarely, but where this number is big, we'll find lots of them, right? Because everything is equally likely, but there's going to be many of these, you know, where we have a particular distribution. So the probability of finding any one distribution among these supersystems probability, curly p, of a particular distribution, M1, where you put in whatever numbers you want here, is proportional to this number. And the proportionality constant must just be a normalization constant because the probability distribution must have the property that its integral is 1. If you add up all the probabilities, you have to get 1. So there's some normalization constant C times this number that we have calculated there. Okay, and now we want to ask, what is the most likely distribution? So if you have all these super systems, and if I were just to choose one at random and look at it, the most likely distribution would be 1, where this is a maximum. So our job to figure out what the most likely distribution of energies is, or the most likely distribution of money in a town, is just to choose the ends here so that this number is as big as it can be. So our problem then is to find the ni's so that this number, which is n factorial over n1 factorial, n2 factorial, n3 factorial, is maximum. That's what we have to do. And now you can see why we need Lagrange's method of multipliers. We have to maximize this number subject to constraints. 2 constraints. All these little n's have to add up to curly n. And all the energies have to add up to the total energy, some constant.
Which energy is non-English expression?
No,
So
it's true. But we will still have a constraint which says that n1 times e1 plus n2 times e2 must equal some constant et. So we'll still have a constraint that we'll have to use when we extremize that. Okay? Now we'll quit here and then we'll start with doing this problem. And what this will give us is the Boltzmann distribution. And that's kind of is at the very basis of thermodynamic potentials, of free energy. Okay? So we'll see how to get the Boltzmann distribution and how to derive the free energy. I have some handouts, so this is the continuation of this chapter.